Hello guys, welcome back to Tax Riders. In this episode of the Applied Numerical Computing series, we want to go to more serious stuff. We want to start to talk about the actual numerical methods. And as the first one, we want to start with the finite difference method and the techniques to solve nonlinear ordinary differential equations. So let's go for it. Okay, this episode we will discuss this for the notebooks, so I open them all, and yeah, more or less all of them. But let's start from the first one. So the first one describes the model, the kind of model that we want to deal with, and as I'm not, I don't want to go to the details of the mathematics and mathematical modeling. I won't discuss it a lot, but the thing is, the model, the differential equation that we want to solve is related to the phugoid motion, a kind of motion. There is a figure here, I think. Yeah, the kind of motion that you see on aircrafts or gliders when they have this kind of going up and down and changing in pitch frequently. And yeah, this is the trajectory of the movement. And for describing this, a mathematical model can be derived. This is actually what this notebook is discussing. So you have the different forces, you have the weight, you have the lift, and different components of each of these forces. So this is actually the discussion. I told you I don't want to go through the details. So this is actually deriving the components and then employing the Lanchester's technique to derive the to derive the equation, the differential equation, or the kind of equation that we can plot the trajectory via the free body diagrams and this kind of stuff. So this is actually more or less using you can see that it's a free body diagram to derive the different components of the movement and of the forces that is applied to the aircraft or glider, and then deriving the differential equation that describes how the trajectory can be plotted, how it can be tracked over time. This is what we are trying to do. So there is an entity here, a quantity, let's say z, which tells us about the the height of the glider, or its difference from a reference height. It can be interpreted as that. But this is what we are seeking for. So by plotting this over time, we can see that, okay, the glider movement is like this. So this is actually how the derivation works. And yeah, this is the final form with some different constants. And there was also a differential equation form. So this one. This is also what later on we will discuss more in details. So this is how it's derived. The phugoid curves can be plotted according to this equation. And then for doing that, you already know that it's quite simple using NumPy and Matplotlib. So yeah, by importing appropriate packages into Python, and then calling this function, which is actually defined in a behind the scenes sort of source code in the phugoid.py. And then by changing different parameters with different trajectories. So these are the different movements that this model can handle. But what matters to us, what is really interesting for us, is how we can model this with a differential equation, how we can solve the differential equation actually. So for the phugoid oscillation, according to the mathematical model, this is the equation that we want to solve. It has, this is in a second order equation, so because we have the second derivative of z in respect to time. And also it is sort of, we say it's non-linear because we have this component. This is according to the mathematical formulation. So if it was, for example, the movement trajectory, then it had two components. One was along the normal axis, one was parallel to the trajectory. So for example, if it was the trajectory like this, then it was different components of that. And then for this reason that we have this this quantity, one of the components here, this becomes nonlinear, and then the solution becomes even more complicated. But it doesn't matter. We go on and you see that how we can deal with that. There are techniques that we can deal with this nonlinearity. So that's the equation that we want to solve. Let's write it in this way. Instead of that, the formulation, we employ this, this notation. That's much simpler. And when we want to deal with this equation, it's important to consider this as a whole, but sometimes it's easier if we decompose it into different equations. So just look at this. If we say that if the first derivative of z in respect to t is b, then b can be calculated like this. So the derivative of b, which is actually the second derivative of z, can be g multiplied by this, which is actually moving g to this side of the equation, and then factorizing that. We saw how we can do this using also simply computing in the SimPy tutorial. And then this is actually the system that we want to solve. So we have sort of simplified the model into this, and then decompose this into these two equations. So we can, target them both at the same time. In order to do that, we define u. So u is something like this, and this is the derivative of u. But you don't need to deal. If you want to, you just ignore the nonlinearity of it. You can just look at this as the concept of the numerical computing that we want to employ. How we can solve a first order ODE, because by doing this, instead of a second order ODE, we will have only one on the first order, because you can see that now it can be written like this, because this is all the equation is all about. So yeah, we even simplified it one step more. This is, crucial in numerical modeling, that you try to simplify things. In this case, it is mostly simplifying the mathematical representation of the equation and not the physical phenomena. So we say that it's a sort of initial value problem, and that was indeed the title of this series, of this video, of this episode, because when we say initial value problems, it's because we have the initial condition. We know we want to track the motion of the glider. Let's say, for example, this is the glider, the position that it starts, and then it moves on, it goes on. And this is called the initial condition. So this is actually the initial value problem, so where the name comes from. So this is the initial condition of the state, and we know that it starts from there. And this is the start that we say that, when t is 0 is the initial condition, and we denote it with u0. But then, we had still u prime as a first derivative of u in respect to t, and we want to compute it numerically, because we cannot integrate both sides of the equation and derive u, because it was nonlinear, and that was a bit complicated equation. So in order to do that, we can use this formulation, this super easy formulation that says that, this is the definition of derivation, let's say. The derivative operator can be written as this: when this delta t, which is actually the different steps, approaches 0. And then, by reformulating this equation can be derived. So, what does it say? This is very important to see what it tries to say, because this is crucial to understand. This is what matters a lot. The thing is, let me clear this. The thing is, by doing this, instead of tracking, just imagine that we have a function like this, this is t and this is u, and this is actually the function. instead of tracking the trajectory, the movement path of the glider continuously, we can divide it into different subspaces, or we can just see, we know that at t0, so this is where t is 0, t0, it is here. But then we want to see after, for example, a period of time which was actually delta t, it reaches here. And then again, another delta t here, and then here, and here. So by doing this, we discretize the time domain. So this is actually the time domain, you see. And then instead of tracking that, instead of investigating that in a continuous way, we investigate it in a discretized way, discontinuous way, sort of. So a discrete way, let's say. And in order to do that, we can employ this formulation. This is a quite cool formulation to track things. So we say that in order to get this at t, the next time step, which is this one, we need the value of the previous time step plus something. And this something is also is a term that we can compute. And generally speaking, this is something that comes from the Taylor series. So if I want to go to the details, yeah, you can write the Taylor series here. So I can do that quickly. So the Taylor series says that the value, that the fx can be computed like this. The f prime at the value of a, x minus a, and then this is the first two terms of the Taylor series. And then if you say that x, instead of saying x, you can say x plus a, and then it becomes like this: fx plus a equals f of it is still a plus f prime of a multiplied by actually x. This is how it becomes. So just compare it with this one, and instead of a, you put delta t, and instead of x, it is actually t, because the t is x here. And then we want to just see the value of u at a later point. At a later point, if we know the value, the function, so this is actually the f and this is x, we know the value of the function somewhere, which is here actually, and we want to see the value of it just a little bit further with the value of a. And this is, what we are trying to do here. So the value of a here, and then delta t here. So this is how this discretization is all about. This is how this is going to take place, and this is quite cool. So we discretize the time domain into n subspaces, into 10 discrete points, and then we track it like that. And we track it using these numerical things. And then numerically, in order to compute it, this is what we can use. So this is what I said, that it comes from actually the Taylor series. This is the same formulation. The value of u in the next time step, n plus 1, equals the value of u in the previous time step plus the step multiplied by f, the value that can be something that can be, that was in the previous time, it was the derivative of f, but it can be anything. So we will see that how in this formulation, for example, in this case, it is b, because we know that that was actually the b. So I write this down because this is quite important for us. We need it later. And then I say that, zn plus 1, z in the next time step equals the value of z in the previous time step plus delta t and the value of b in the previous time step. I just write them down in another color to say that, these are quite important. Let me correct this, sorry. So this is n. And then the value of b in the next time step equals the value of b in the previous time step plus delta t multiplied by something. It doesn't matter. This comes from the formulation zt multiply. But this is actually the value of z in the previous time step. So this is what it's all about. And then this is, I think I forgot to say that this is Euler's method. this is using the Taylor series or the definition of derivation to track things in a numerical way. And this is this is very famous to be called as Euler's method. And you should also pay attention that U actually was the Z and B. So this is something that we need to track. I wrote it here because we need it later on, and I want to show you how it works in action. And yeah, this is the way that we initialize the simulation. So you can look at this as a simulation. So these are the initial condition, and then we define the U as the NumPy array, which is actually Z0 and B0. So it has only 2 components at each point, and then we say that Z is actually the zeros of n, because we want to discretize it into n time points. And then this is the actual work, and this is as simple as this. And if we want to demystify this, you can say that it says for n, because we wanted to say in n steps. So just look at it as in this way, that this is a t, and then we want to see that, okay, in this value, this is t0, and then it goes to t1, and then t2, and then it goes to, for example, tn. And we have the value at t0. This is an initial value problem. And then we compute the value in t1, it is u0, and then u1 depends on t0. And then we compute the value at t2, which is actually u2, according to the value of u1. And then we go on and we calculate the value at each time point according to its previous time point. This is what is happening here. So we say that the right hand side, you remember that it was u, z, and b. So this is z, and this is the definition of b. You can see it here. And then the u, this is the famous Euler. This is the famous Euler method, the Euler equation. And then Zn equals u0, because u0 is actually u0. This is indeed a NumPy. When you say u0, this is a NumPy array, and u0 means the first component. Just make sure to check out the NumPy video if you have some problems with this kind of notations. So we have simply implemented it, and then if you want to plot it, yeah, let me erase these things because they will remain on the screen. So if we go for plotting it, yeah, this is actually after we have computed the different values of u, we can easily compute z according to that, because we have computed z. That was the first component of u. This is still something that you need to check out the NumPy array, NumPy video to understand how it works in action. And according to t, and then we can simply plot the trajectory path of this glider over time. And this is just as simple as that, but you can see that it is very powerful. The mathematical formulation was a bit complicated, but in action it's easy to implement it in using these numerical methods, let's say. And then in this case it's a bit, we can say, feasible to calculate the exact solution, and this can be useful for us. For partial differential equations, it's not possible to do this. Maybe in very simple cases, but usually it is not possible. But when we can have it, then it allows us to check whether our implementation of the numerical technique works correctly. And this is indeed the value of the z exact. This is simple to compute using NumPy. And then here we compare it with the value that we have derived. So this is actually the numerical solution and then the analytical solution. And you can see that the numerical method, the numerical implementation, is able to replicate and reproduce the output, the real real physics behind this motion. And this is quite impressive that it's possible. It's super nice. And then another thing that is important is computing the error in convergence. This is a concept, a sort of concept that we will see a lot in this episode, and also later on when we want to do some sort of modeling works. So the way that we compute the norm or the error, so this is called a sort of L1 norm, because this is actually the p, and when the p is the power of this term. So when it is 1, then it is the L1, and if it's 2, it is the L2. So we say that this is the first norm, or norm 1 of this thing. So let me clear this, and then yeah, this is the way that we can compute it. So we compute, we have the exact value, so we can compute the error. And then by computing the error, we can plot to check that, okay, with this time step, because for the time step, it's really important that, as I said, when you go on into different values, this is really important that how you choose the time step, because you just ignore all the things that are occurring in this period of time. So if you choose it, smaller, then you capture more things, more interactions. So this is very important. And this is actually a sort of study on that we compute different delta t's, different time steps, and in the value of time steps we compute we perform the simulation again, and then we can plot the L1 norm versus time step. And you can see that, yeah, it is something that tells us that the less time, the less value you choose for time step, the less error you will get. But still, you can see that how it evolves, how the kind of error that you should expect according to the chosen time step. Because obviously, if you choose a smaller time step, it means that, yeah, you should run the simulation longer because it consists of more time steps, let's say. And then in a third notebook, it's full phugoid model. You can go through this. I don't want to go through the details because this is again a kind of mathematical formulation. But in the end, we end up with more complex model. And then using the same techniques, because now you can see that the more trigonometry into the equations. If you wanna solve it using exactly the same techniques with the Euler's method, we can employ it and we can solve the equations no matter how complex they are, because Python will take care of the rest. You just need to know the Euler techniques, the way that you need to derive the equations. In this case, you can see that they are actually like this, and then using a vectorized form, and then yeah, just implementing it. This is quite simple. And then yeah, by implementing it, choosing the correct coefficients and values, so everything is exactly the same, just the equations are a bit more complex, or they look more complex. And then by plotting that, you see that this is actually how it's actually solved for the full model. But then a simple study on grid convergence. Again, in this case, when we say grid, because grid is a term that we use for space usually, but in this case, because we have some quantities that they depend only on t. So u is actually the function of t, only time. And when we talk about the time, when we talk about the grid, it means that the grid that discretizes the time domain. So this is important to pay attention to. And here is again computing the L1 norm or L1 error, let's say. And in this case, we want to compare the L1 norm if it is if delta t is small or delta t is big. So this is the term that is called usually coarse and fine, and fine, coarse and fine, when it is when this is actually a sort of coarse mesh, let's say, for t. And when you do that like this, so smaller time steps, then it is called a fine grid. This is the terminology that you will find in lots of numerical modeling works. And this is a similar thing to what you saw. and shows the L2 norm of the exact and the numerical solution when you have a smaller delta t and when you have a larger delta t. And the reason you can guess is because when you have a larger delta t, then you just ignore all the interactions, all the phenomena that are occurring inside this time step. And this is why the order convergence is a term that can be used for this kind of stuff. And then in the last notebook, it's an introduction to more advanced techniques, because Euler methods is a first order method because you have only the first order of derivative. It was like this, equals un plus delta t u or f of u. So here you have only the first, and then for the rest of the Taylor series, let's say, then you had, for example, the second order of the derivative terms here, and we just ignore them all. So that's why this is called a first order technique. So Euler was a first order technique, but we can employ the second order the third order, this kind of stuff, and it just means that we employ more terms from the Taylor series into account, and then it means that we have more accurate numerical schemes or numerical representation of the mathematical equations. So for second order methods, there are quite some techniques. And the Euler method can be actually modified to represent that. But when they say midpoint, the term midpoint here that is actually used for Runge-Kutta techniques is because instead of discretizing the time here, that is, you say that it is t0 and t1, then you say that I have another middle point here, which is actually t half, and in order to refer to that, they say tn plus 1, and this one becomes tn plus half. So this is, you can consider this point as well into your computation and all the calculations that we do. So this is why these techniques are usually called higher orders, or with this term of midpoint. And you can see that the formulation is a bit different. And what is nice here to discuss, I don't want to go to the details of this, but Runge-Kutta is the second order. I just want to show you something very beautiful, very nice here, that why we go for higher order techniques or more advanced ones when Euler is very easy to implement and is quite nice and pretty simple. So why should we do that? And here it's a sort of implementation of the Runge-Kutta. For this, a second order technique, everything is the same. This is the same code. Euler step is what we saw before. And then the L1 norm. And then the Runge-Kutta step. This is a bit different. You can see this scheme is a bit different. And then it's a sort of, comparing the solutions. So the solutions are exactly the same. We expect them to be the same. Let's see. Yeah, these are, you see that the trajectory is exactly the same. But the thing is, for grid convergence, the grid convergence study, we see this kind of, curve that shows us, you can see here, that with this order of delta t, we have an error, in the order of 10 to the minus 4. And then I just go back to the previous notebook for the grid convergence of it was here. Yeah, this is the grid convergence for the Euler method, and you see that even for a super small time step, we have still error in the order of 1, let's say, and a bit smaller. But for the Runge-Kutta, you can see this is the care for the Runge-Kutta, as I said. For Runge-Kutta, you can see that in order of 10 to the minus 2, we have a very low error. So this is actually why we go for higher orders. So you see that they are super efficient. They are, let's say, more efficient in comparison to first order techniques or simpler ones. So the difficulty here is to choose between the simplicity and you know, less efficiency, and also a bit more complicated implementation, but higher efficiency. So this is actually the reason this is very nice to compare these two curves and see that, yeah, this is for the rank CUDA for the second order technique, and this is for the first order technique, showing why this is crucial to consider higher order methods to improve the convergence of the numerical scheme. And yeah, this is actually what I wanted to discuss for this. I think, yeah, by going through all the things that I said, you can say that you have a good working knowledge of this. But if you want to know more about the details of this mathematical modeling of the derivation of the mathematical formulation, and also solving the full model, you can go through these notebooks. Make sure to check them out. And I said in the very first video, you can download this and run the codes yourself and try to modify the codes. This will help you definitely to learn it much better. So feel free to whatever you like, whatever you prefer. It depends on the time that you want to put on this, and it depends on the level of knowledge that you want to obtain, you want to gain from this course. I hope you enjoy that. See you in next videos. Bye.